All right. So let's go over the problem real quick from that was due today. It was another shortest path problem, right? So you know what? Rather than typing in a bunch of data all over again, I am just going to go ahead and open what we worked on in class on, what was that, Monday? And then modify the values that were in there. So let me get Open Solver up and running, and we can open recent. So what was the 24, wasn't it? All right. So help me out. What was a problem that was due for today? 623. 623. All right. Okay, so it's got one more node, right? So we'll put 7 and 7. Whoops, 7 here. All right, and then let's put these in. So 1 goes to 2 at 7. 1 goes to 3 at 9. 1 goes to 4 at 18. But it doesn't go to 5, 6, or 7, right? Where does 2 go? 2 goes to 3 at 3. But not 4 and 5. It goes at 5, right?
Yep. 6 and 7 are not they're very expensive.
Just as a note here, if you find this hard to read, one thing that you could do is you could highlight all of the ones that are part of it, and you could change the text color, make it a little bit easier to read, if that would be helpful to you. All right, so 3, what does 3 connect to? 2.
Yep.
And 5. All right, what does 4 connect to?
6.
Just 6, huh? And that's at 3. Oops. What does 5 connect to?
2.
At what level? 5, okay.
3 at 4.
But not 4, or itself.
6 at 2. And 7 at 6.
All right, and 6 connects to
5 at 2.
and 7 at 3, right? All right, so let's go ahead and
What was the keyboard shortcut for that?
What's that?
What was the keyboard shortcut for that instead of like dragging away the whole?
Control C copies and Control V paste.
You just copy and paste. Dang, I'm a stupid idiot. I'm so dumb. I'm so stupid. You're so stupid. No, I'm so dumb.
All right, let's move these over. There we go. Oops. Then we need to make sure that these are right here, right? So the sum H. Right, so we got C17, so C12 through C18. right, so we're all right, so what's wrong with this?
This 7th row is still.
That's not the problem.
Out there. It's not in the 18th row.
There we go. So let's update our model then, right? So our objective cell doesn't change. Our variable cells do change, right? And our constraints change. Yeah, but this isn't right. Right, this should be so that we're C16 through C. Oh, that didn't work. These are all wrong. This is C12 through 18, right? But this should be D12 through 18. This should be E12 through 18, right? And this should be F12 through 18. And this should be G12 through G18, and this H12 through G18. All right, let's see if I quickly did that. Does that look right? So what is this path? What is this path here? Make sure we see this. So we start at 1, so we go to where does 1 go? It goes to 2, right? So now we go down to 2. Where does 2 go?
2 goes to 5.
It goes to 5. 5 goes all the way to 6. 6 goes to 7. Okay? Now, I want to point out something that's interesting. Notice that we have whole values here. But there's nothing in this model where we said you have to put a whole value in here. That's actually, when we start talking about Chapter 7, we're going to actually add those as future constraints. So if you think about some models where you're doing something like airline seats, you can't reserve half of an airline seat. If you're trying to schedule people, you can't schedule half of a person to work a position, right? So there will end up being constraints that have to be what are called integer constraints. It turns out that this problem we don't have to add those constraints in because of how the situation works, right? Why would we put half of our simulated product that we're shipping on one channel and a half of part on another? If one is less expensive than the other, wouldn't we send all of it on that less expensive route? And so that's how we don't have to worry about having a partial value shipped between these different things, because it's always going to ship via the least expensive route that it can find, and it's going to ship everything via that route. So that's why we have this pseudo product that represents us at the start location, and the pseudo demand that represents us getting to that final location there. Yeah, Will.
I have a question on the columns I and J, why it works that their sums have to equal each other.
Okay.
Or like, if that's all it is, right? It's all just
yes, because of what we set them to be. Okay. So this column, right here, column I is B12 which is this value, right,
Okay.
through H12.
Yep.
So if I click on that, what does that sum represent?
The total times.
What does this blue rectangle represent right there?
Total out of 1.
Everything that 1 is shipping out, right? Because we say that this is what is going out from this destination, from this source to these destinations here. So this is what goes from 1 to 1, which doesn't make sense. But this represents what goes from 1 to 2, and then 1 to 3. So if we sum them all together, this represents everything that leaves 1. Okay? And we do that same sum for this whole column. Right? This is just, instead of line 1, it's line 2 right here.
Okay.
Right? So that is true for these first 6. They're just those sums of those lines. This last one, we hard code in a 1 here, and we'll get to that in a second. Just like we have a hard coded 1 here that I'm going to pause for a second and skip to this next one here. Right? Because now it's a column. What does this column represent again?
That represents in of 2.
Yeah, it's the in of 2, right? Because this is what comes from 1 to 2, from 2 to 2, from 3 to 2, 4 to 2, right? So this whole column represents everything that comes into 2. And we do the same thing for all the rest of these. We do each column. We do D, then we do E, and then we do F, right? So this column, these values right here, represent everything that's leaving a value. And these values here represent everything that's coming in to those. And so when we say that they're equal to each other, we're getting that no net aggregation, right? That the inflow equals the outflow. That we don't want to store anything at one of these nodes. We want to pass through the node. So everything that comes in has to go out. So that gets us nodes 2 through node 6. What it doesn't give us is this top one and this bottom one here, which have those hard-coded values. But now if we think about it, we said that this right here, this value, represents everything that 1 is sending out. Right? What do we want to send out of 1? We want to send out that mythical 1 unit. So we just hard-code this 1 in here. So that's why those can be equal to each other. And now if we go down to the bottom row, our hard-coded value is right here as a 1, and this represents everything that's coming into 7, which again is the demand constraint. So the previous one was the supply constraint. This is the demand constraint. We want to make sure that 1 comes into the 7th element in our graph. So as a result, we can just set all of those rows equal to each other because of what we did for this special situation here, this special situation here, and these are the general purpose ones in between. So we could represent it with a single constraint. It's in the model. Actually, it's not one constraint, right? It's actually 7 separate constraints. 1 demand constraint, 1 supply constraint, and 5 no net aggregation constraints. But we can, inside of our model, because of the way we ordered them, we only have to enter it 1 time because it's a range inside of Excel.
Okay. And so if we wanted to change this calculator for traveling from different nodes to another one, all we would do is hard code their in and outs.
Yeah, very good question. So if instead of starting at 1 and ending at 7, but we wanted to start at 2 and end up at 4 or something, yeah, we would change what this hard-coded value is here and here to match the right node.
Okay.
Mm-hmm. All right. So let's, if you have your books open, I want to look at section 6.5. which is going to look a lot like what we just did in, let me save this before I forget, this is 623. This is going to look a lot like the shortest path algorithm that we just went over. But instead of doing shortest path now, what we're going to do is what's called a maximum flow. Okay, and this is really helpful if you're thinking about any company that operates networks. So that could be information network or a communication network like a phone company, or so AT&T or Verizon might do this kind of analysis. But it also could be a physical network like the transportation network. In other words, the roads that you travel on. And what we're trying to do is we're trying to say how much stuff can get through this network. If you're an airline company, do I need to add another route into my system to be able to facilitate more flyers going through the system? And so on and so forth. So what we're trying to say is how much possible people, how many possible communication packets, how many possible cars, whatever the network is, whatever is traveling on that network, how much can we get through it to a maximum? And so what we're going to do, I'm not going to draw out a full network here, is we might have something that connects like this. And this is our starting node. And this is our destination node. If this is what we're trying to do, what's the maximum amount of people that we can get from here to here? The trick that we do to turn this into something that we can solve with our linear problem is we're going to make a fake link that reconnects that destination back to that start. Okay? And what we're going to do is we're going to say how much can we pretend that get from here to go all the way back to here. That is going to be the flow that gets through this entire thing, because we can't send something over here unless it got to the destination. Okay? So this is not a real link. It doesn't represent a real connection between the source and the destination. And what we're going to do then is this is going to be one of our variables that we can affect. And what do we want to do with that? What do we want? The name of the problem gives a really good hint. What do we want to do with this flow? We want to maximize it. So this is going to be our objective function value. Okay? So let's think about what we do. Instead of what we've done so far, where we put some fake number of cars here, let's say this is a transportation network, what we're going to do instead is we're going to treat all of these as our distribution center, where we want no net aggregation. So everything that comes into this node better go out of that node. And that's going to be true here for this start node as well. Everything that comes in, which is the flow, needs to be what we send out here. Okay? So we can only send out of the start what got all the way to the very end. We can't just send a million cars here if there's no way to get a million cars over here. Okay, so we're going to be limited by how many cars we send here by this flow. And this flow, since it's the output from this node right here, is going to be limited by what can come in to it. So every time we're going to try to increase this flow, that's what our solver is going to try to do, make this flow bigger. If we make this flow bigger, that means we can put more traffic on here, which means we might be able to get it through and get it back to the destination. If it does, great, we've got a higher maximum flow. If it doesn't, well, then it's not a solution to our problem. We can't get that maximum flow through our system the way we wanted to. And so it won't raise it up to that next level because we'll have more coming in than we can send back out here. Okay? Does this make sense? So it's not a real link in our system, but we add it to our model to be able to measure this. So let's take the flow from figure 616 as an example here. So again, we have 7 nodes in our system. So I'll just do it 1, 2, 3, 4, 5, 6, 7. And we're going to do the same thing we've done so far. And to make it easy for myself, I am going to start off as if they were all disconnected. And then I'll only put the connections into the system. So we know that 1 goes to 2 at a level of 5. 1 goes to 3 at 6. And 1 goes to 4 at 5. How about 2? Where does 2 go? 2 goes to 3 at 2. And 2 goes to 5 at 3. All right. How about 3? 3 goes to 2 at 2. 3 goes to 5 at 3. 3 goes to 6 at 7. Okay, I want to pause here for a second because my wording might be confusing here. These numbers are not like they were for the shortest path. These are not distances. These are capacities. In other words, how much stuff can get through. So what we're saying here is when we're looking at the pipe that connects 1 and 2, we can get 5 cars through the system there. Right? That's what that 5 represents, is how much can get through the network between those 2 different places. So if my wording was confusing because I was at, I apologize. So 4 only connects to node 6 with a capacity of 5. Let's see here. 5 connects to 6 with a capacity of 1 and a capacity to 7 of 8. 6 connects to 5 with a capacity of 1 and to 7 with a capacity of 7. And now, this is where we see the big difference between our shortest path algorithm and this maximum flow algorithm, because we're going to make this pseudo link right here from 7 back to 1. Right here. Yes?
Do you need one from 3 to 4? Isn't there 3 there?
From 3 to 4, yes, thank you. And that's a 3. Yeah, 3 is very heavily connected, isn't it? Okay? So I'm going to delete this value here, okay? Because we don't know what the capacity is. All right? All right. So, actually, you know what I should have done? They shouldn't have been zeros because there's not costs. So, that's our capacity. And so what we're going to do is we're actually going to put 1,000 in here. We don't know what the capacity is going to be. Okay, so this is our capacity chart right here. And what I'm going to do is copy that down here. And now I'm going to delete all these values here. All right, so let's see what we want to do here. So, our objective cell, we know we want to maximize what flows off this mythical link right here. Well, where is that amount of flow? Well, that's all the way down here between going from 7 to 1 right here. Okay, so that's what we want to do. That's what we want to maximize right there. Our variable cells are all of these cells right here. The ones that represent sending from one of these to one of these locations right here. So we're allowing it to change any of those 49 cells, right? 7 by 7. And one of those is also our objective function. Okay? So now let's think about our constraints. What are our constraints going to be? Yeah,
I have
Nathan.
a quick question. Can we also have B8 be the can we maximize?
No, because this is the well, I suppose you could, yes. If you made that a variable and maximized it. Yeah, you could do that. Okay? So in this case, we don't have a value that represents our demand or a supply. So we're not going to have our demand or supply constraints, but we're still going to have all of our no net aggregation. In other words, our inflow and our outflow needs to be equal in all these things. So what we don't want to do is we don't want to send a car here and then just stop it. Right? We want to send it and keep it going all the way through to the end. So whatever sends in better also go out one of the links that it's connected to. So for every node, including our start node and our destination node now, we want to have everything that comes into them also leave them so that we get as much through the system as possible. Okay? So in this case, I'm just going to do what, again, does this row represent? We saw this in the last one. That's not what's coming in, right? Because this is, 1 is the source. So this is from 1 to all these things right here, right? So this is the outflow right here, which is B13 through H13, right? That's the outflow of that row. Right, so we get the outflow of each row, and then the inflow is going to be this column, right? This represents everything that goes from 1 to 1, 2 to 1, 3 to 1, 4 to 1, right? So this column right here represents everything that's coming in to node 1. Okay, so we know we want those to be equal, right? So we want the inflow to equal the outflow. Okay? But we're not done, right? What's missing here? If all we did is said the inflow is equal to outflow, what could we do that's problematic? Right, we could put as much cars along the track as we want to, right? We need to somehow take this into account, right? This is our capacity. We cannot exceed our capacity. So what does that sound like? What kind of constraint does that sound like? Say it louder. I hear whispers. Severance tenant. I heard the right whispers even. Huh? Yeah, well, it's kind of like demand, but I'm talking about, is this a less than or equal, an equal, or a greater than or equal constraint? Less than or equal, right? We want these values here to be no greater than these values here. Right? So let's put that in there. So our values that we're doing, we said, are going to be less than or equal to the capacity that we have available to us. Okay, right? So you can see that we've got these green boxes that represent the capacity. We've got the blue boxes that represent the outflow and inflow, and we can now go ahead and solve it. Okay, fine. We'll put a value in there. All right. So we have a solution here. We can get 14 cars through this network maximum. Okay, and you can see how much we're going to do. So for instance, we're going to send 3 from 1 to 2. We're going to send 6 from 1 to 3, and we're going to send 5 from 1 to 4. That better equal 14, right? Because everything goes through that starting location. 3 plus 6 is 9, plus 5 is 14. That's good. And we can also look at 7, where we have 7 coming in from node 5, and 7 coming in from node 6, for a total of 14. Okay, that's good, because that's the final destination. So we have 14 leaving, we have 14 arriving. And so we get 14 through. If you look at node 5 to 7, there's actually capacity for 8 right here. So the road could handle more traffic. But the problem is not that the road from 5 to 7 couldn't hold the traffic. It's that we couldn't get the traffic, we couldn't get the cars to that road. Right? So this helps us identify where the bottlenecks in the network are. Because we can look at our binding constraints, right? And we can see which ones are binding. Right here. All of these are the ones that have shadow prices, right? Those are our binding ones. So those are the connections that we would want to increase in order to increase flow through our network as a whole. So rather than doing something like, I think we should make this road bigger, and spending millions and millions of dollars doing that, we can analyze what the model says and says, no, this segment of your network, that's where the bottleneck is, that's where you should spend your money. Right? So it allows you to do wise allocation of your money and not just guessing where that allocation should be. Okay? Does this make sense, this max flow problem? All right. Let's look at one more example type problem. If you turn to problem 622, we'll use that as an example here. So let me save this. This was okay. This problem is what's called a redistribution problem. So this problem is something that you might see if you go to some sort of rental company. Especially think of like a U-Haul or Enterprise. You know, both are rental vehicles in those cases, but to do different purposes. If you rent one of these vehicles and you return it back to the starting location, they can make sure that they have enough inventory at that final location. And so they're going to have some generic price that says the rental costs this much per day. But what gets difficult for these companies is when you rent these cars and go on a one-way trip, right? And you start in one location and you end up somewhere else. That's going to deplete their supply from where they need it and increase their supply where they might not need it. Okay? And so we need to then be able to look at our forecasts and the demand and supply that needs to be, and we need to redistribute our resources back through our network in the most efficient way possible. We might actually have to hire people to drive those cars back to their original location. So we want to minimize how many people and how many cars are being driven all over the place just to get back to the demand needs that we expect in these situations. So for this example, for what did I say, 622, each node in this case has either excess capacity or insufficient capacity, right? It has demand for more cars. So for instance, if you look at node 5, node 5 has a +2 by it, which means that there are 2 more rental vehicles at this location than we expect to need. Okay. Versus if you look at location 1, it has a -8 next to it, which represents that they expect to need 8 more rental vehicles than we have available to us. Okay? Does what the graph have on it as information make sense? Or are there any questions about what information is in this graph? Okay, so let's think about what do we want to do. English objective. What do we want to do when we redistribute these cars? What's our objective? Yeah.
Minimize our places where we have less than we need.
Okay, so hopefully we've got the right inventory. So in the end, we should have all zeros there, right?
Yeah.
Okay, so if that's our objective, what are we going to minimize or maximize in order when solving that? Because in the worst case, I could just send all the cars to 1, and then ship some to 2, and then ship them to 3, right? That's a bad case. What do we want to do?
Either minimize the number of cars you have to move or minimize the number of movements.
Right. So there needs to be something associated with the movement, right? So in fact, we don't have what's called a fully connected graph. We can't get from all locations to all other locations. So it's going to cost sometimes a lot of money to transfer a car from New York to LA, right? So maybe we send something from New York to St. Louis and something from Portland to LA, right? And so we want to minimize the costs that are associated with moving these cars. Okay, and so if you look at the edges, these represent costs for us. It could be time, it could be actual dollars that it costs to send it there. It could be a distance. Okay, whatever it is that we care about for our purposes, we want to minimize those costs. Okay? So, let's think about, we don't have it on our example, but let's think about the node that has a 0 by it. It doesn't have plus, it doesn't have minus, it has 0. Okay? What should be true about this node? About the cars coming and going from that node? Why?
Because you don't need more lanes.
Right. So is it okay to send cars here?
Yeah.
What do we need to do if we send cars here? We need to send them somewhere else, right? What does that sound like? It's that same kind of like idea that we've been doing at the distribution center. We don't no net aggregation there. Okay? How about this node where we've got a -8 here? What should be true about it? We better end up with 8 more cars coming in. Then is it okay if we send cars out of this? If we send 2 cars out of here, what better be true? We better receive 10, right? Okay? So just because we have a negative here doesn't mean we can't ship cars out of it. It just means that we need 8 more cars to come in than we ship out. Okay? And then by analogy, what should be true for this positive one, this 2 right here?
Send 2 more out.
Yeah, that we send no more than 2 cars out than we receive, right? So is it okay for this node to receive cars?
Yes.
Yeah, there's nothing that says we can't do that. We just need to ship even more cars out then to make this equal distribution. Okay? Does that make sense, what we're trying to do at each of these node types? Okay? You can kind of think of this as being like a demand node of sorts. A supply node. Because we have excess capacity. And we can think of this as being like a demand node because we need capacity. And so what we can do then is we can go and make supply constraints, demand constraints, and no net aggregation constraints for each one of our nodes here. All right? Does that make sense, what we're doing? So let's pick one of the nodes in our example here. Since I don't have it written on the board, refer to your book. But let's pick one that's not too crazy. Let's pick node 7. Okay? What should be true at node 7? What's its value? It's at +6, so it's going to be like one of these supply, right? So let's do this in, out. What is the input into node 7? Which connections do we have into node 7?
2 and 6.
2 and 6. So we have x 2 to 7, and we have 6 and 7, right? That's the input into node 7. Okay, what's the output from 7? What can 7 send? Where can 7 send its cars to? There's only one place, right? Where is that? 4. So x 7 4. Okay? And we said that we can send up to 6 more out of here than we receive in, right? So let's do out x 7 4 minus our in x 2 7 plus x 6 7. That That make sense? We can send up to 6 more out than we receive in. Okay, let's try node 1, because that's a negative. We have our in and out as well there. What's the input to node 1? What comes into node 1? It's just 3, right? So that's x 3 to 1. Where can node 1 send cars to? 2 and 5, right? So x 1 2 and x 1 5. Now the case here is not that we can send extra out. Here is that we need to have extra in, right? So if we do our in minus our out, that needs to be 8. Right? We need to make sure that we have 8 more coming in than we have going out. Right? So 1 could send out 2 here, then we'd better receive 10 on this line right here. Yeah, right.
Why was the 6 not equal?
Because it's okay if we end up with excess. It's not okay if we end up with a deficiency, right? So we don't want to ship cars if we don't have to. We only ship cars if we need to. If these were both less than or equal, then it would be a problem, right? Because then our cost would say, well, then let's keep them as they are. Let's not ship anything. But this less than or equal rate here allows us to have a little bit of extra capacity somewhere in our system and only send some cars that that absolutely meet the demands that we have at any given time. All right? So now what you would do is you would do this for all 7 nodes in your system. All right? And we'll see how to do that in class on Friday. All right? I'll see you guys then. Yeah, just...